Okay, time to begin. For today's lab, I'm going to start with a lecture for about an hour, and then we'll get into the lab. The material that will be on the first exam, because our first exam is 1 week from today, should cover through what I talk about in class tomorrow, but not Friday or Monday. Tomorrow should be electromagnetic waves, and then that's the end of the cutoff for the exam. So today we're going to talk about inductance, so we can do labs on inductance. So I'm sorry, I still have the AC impedance here. Yeah, Diksha.
So just to clarify, so for the test next week, it's going to be chapter 22 and 23. Right?
It's going to be through chapter...
Because you've already covered 22, and I'm guessing you'll finish 23 tomorrow?
No, I'm finishing 23 today and 24 tomorrow.
Chapter?
I'm pretty sure it's 24 that I'm covering tomorrow.
All of 24?
Yeah.
It's only 4 sections.
Yeah, it's short.
Okay.
Yeah, it's.
So we have all the concepts for 24 then by tomorrow done?
Yes, you should have all of the concept coach questions through chapter 24 done by tomorrow. Okay, thank you for clarifying. So we're going to talk about AC impedance, but first we have to talk about inductors. So American scientists, we always like to be able to have American scientists because there aren't that many of them that we discuss. And this here, Joseph Henry, he's an American, so I guess it's Henry, not Henri or something like that, was the first to do a lot of things with electromagnetism. He was the first to do something I've done as like a little children's story at church, where you have a little nail and the nail can't pick up anything. That's like you trying to witness to people when you don't have God in you. But then you wrap the wire around the nail and you connect it to the battery. That's you connected to God. And then it'll pick up all of the little paper clips. Yeah, it's a good little children's story, right? He was the first one to do this. He probably did not do it as a children's story at church. But he also was the first person to talk about self-inductance. Now, we've already learned Faraday's law of induction. Faraday's law of induction says that you have an EMF induced if you have a changing magnetic flux. Now, that EMF that's induced can be produced by the magnetic field you create by making current go through your original coil. So that's why it's called self-inductance. When we did the transformer yesterday, that was a mutual inductance. We had current going through one coil, creating a magnetic field which is coupled to another coil. You might have noticed the inductors usually had an iron core that went from one coil to the next coil. The reason is the iron coil is going to make the magnetic field strong, and very little energy will be lost from one coil to the next. You'll have the same magnetic field in both of them. And so that's what gives you a high efficiency. The same thing will actually be true for a self-inductor. We'll probably usually put a piece of metal in there so that you have a stronger magnetic field that you create by making current in the coil. But then the change in that magnetic field will induce a current in the coil. So you put a current in and it induces a current back, or an EMF back. So sometimes we call this a, quote, back EMF. So if you have an electric motor that you're putting current in, it starts to rotate because you put the current in. But as we said, the electric motor and the electric generator are the same device. So once it starts rotating, it starts generating power that's opposing the voltage you put in. And so we call that a back EMF, and you can calculate it using Faraday's law of induction. So if I just have a single coil of wire, I can also have a back EMF and induced voltage because of the change in magnetic flux. So this was what Joseph Henry determined. Here's what some inductors look like. Here's what the inductors you're going to use in class today look like. The big block here. That big block is just a bunch of wires wrapped in a circle around a piece of iron at the center. But these here, like, my boy had to, he's a sophomore in high school and taking a college class. It's a really low-level college class. But for his class, he had to just rip apart a computer. And one of the first things you see is something that looks like that. That's an inductor. He looks at it and says, what is that? He did not ask this. I wish he had. Is that a lifesaver? No. That is a bunch of wires wrapped around a loop of iron. This here looks a lot like the ones you're using in lab today, and you can see some other designs. They're used in lots and lots of circuits, and we'll see why in just a few moments. You probably also noticed there's 36 slides here. That's both the lab and the lecture part. So let's get to Faraday's law of induction had, and I'll write it again up here. That was Faraday's law of induction. Now we could rewrite that. If you make an inductor, you're not going to have the number of loops changing. So I can put the number of loops inside my delta. So that's just another way of writing Faraday's law of induction. And so this thing in parentheses we define as the inductance times the current. Now you might ask, how in the world do we come up with something like that? People in the class this morning saw the derivation carefully. We'll see it a little less carefully, but we'll see it. But the inductance L, so L is our symbol for inductance, times current is equal to the number of loops N times the magnetic flux. Now the units of magnetic flux. I usually make a really big deal about the units of magnetic flux. Why? Somebody paid attention, right?
It's a Weber.
It's a Weber, and that's close to Webb. Now, it's not nearly as cool as the Webb telescope that's supposed to blast off in, a year and a half. That's named after James Webb, but it's Webb, not Weber. But the units for flux are Webers. So the magnetic flux, which is B times A, so that would have units of Tesla times meters squared. That is equivalent to a Weber, WB. And so if I look here, N, of course, has no units. So my magnetic flux is the units of inductance times current. So that means my inductance is going to have units of Webers per amp. That's right, you see there. Webers per amp. And if you go through Faraday's law of induction, you have voltage on the left side is equal to Webers per second. And so divide top and bottom by second. So we have Webers per second, i.e. voltage, divided by amperes per second. Well, then you put the seconds on top. And so 1 Henry is a Weber per amp or a volt second per ampere. Now, I don't care for you to memorize this. Certainly, I have not. But you should just be able to logically go from equation to figuring out what the units of a Weber are and what the units of a Henry are. And like I said, I don't have those memorized. I don't expect you to either. So we have those units. And now let's see where this comes from. So Faraday's law of induction, the voltage is minus N, change in magnetic flux over change in time, which is minus L, change in current over change in time. Well, if you look at the equation for inductance, inductance for a solenoid was mu. Now, if I have something like iron in there, it's going to be mu for iron, the permeability of iron rather than the permeability of free space, times N squared. Remember, N is the number of turns per unit length, times pi r squared. Pi r squared is the area of a circle, times the length. Or if you substitute the number of turns instead of lowercase n, you have this equation. That's the physical inductance. I didn't show you where it came from. I forgot. I didn't show you in this. I took those slides out when I was preparing because I figured it would be too long of a lecture. Let me go back and do it very, very quickly. You have a solenoid. So the magnetic flux of a solenoid is going to be the magnetic field of the solenoid times the area. Remember, the flux is magnetic field dotted to area. But for a solenoid, the area is always going to be parallel to the magnetic field inside. So B dot A is just BA. The magnetic field is mu naught Ni. So there's the magnetic field. And the area, of course, pi r squared. So that's the magnetic flux. So if I put this into this equation, I will have my voltage is equal to minus N. Everything that's constant I'm going to bring out, mu watt, lowercase n, pi r squared, times change in current over change in time. So this here must be the inductance. But notice I have mixed units, capital N and lowercase n. And so I have to convert one. So using lowercase n is equal to capital N over L, then I have and then I can combine these two n's to make that an n squared. Whoops. My erasing is getting sloppy. And then I have this here as my inductance L. So that's where it comes from. It's not a super hard derivation. You can see you create the magnetic field by having current going through the coil, and then the changing current had a changing magnetic field resulting, which induced a voltage, and L here is the thing to link between the changing current, the rate at which current is changing, and the voltage that's induced. For our sign conventions, it's always important to know what direction is the positive side and what direction is the negative side. Remember, we did this with resistors. We said for a resistor, if I have a resistor and current's going like that, which side is positive, the top or the bottom? The top. The side the current entered is positive, the side it went out is negative. We maintain the same convention if we have increasing current. The direction the current's going has the same sign conventions. And if it's decreasing, well then you have a negative for the delta I over delta t, and that's what changes the sign. So you draw your plus and minus signs the same way. Now why is that going to be important for today's lab? Because you're going to be measuring the voltage drop across the resistor, the inductor, and the capacitor. And you need to know which side to put the positive of your voltmeter on. And so by using this, you say, okay, if the current is going, if we go back to the first picture, we had a resistor, inductor, capacitor connected to this thing here is an AC power supply. If we say the current's going like this through all of them, then it'd be plus minus, plus minus, plus minus, using the same sign convention for all three for how you connect your meters. So that's why the sign convention is important. If you don't have that, you don't know how to connect your meter. Now, an important thing about the inductor, what does an inductor do? An inductor is kind of like a capacitor. A capacitor stored energy in the form of an electric field. Or we could say it stored energy in a charge separation. With the inductor stores energy in a magnetic field. We don't have a charge separation. We can't do something like that for the inductor. It's purely storing energy in a magnetic field. You make current go through a coil, energy is converted into the magnetic field. You stop forcing current, that magnetic field diminishes, but Faraday's law of induction says that change in magnetic field is going to make a current. And so the energy that was in that magnetic field is returned, making current when you stop pushing current through it. So inductors store energy in a magnetic field that's proportional to the current. So, this started with the power provided by a source is the voltage difference times the current. So at any instant, the power being produced is the voltage, EMF here, multiplied by the current. So we can calculate average power if we take current and ramp it from 0 up to a maximum value. So this equation here is actually, it's derived by saying, let's take our power is equal to E times I, and let's ramp it up and find what the average is. And just like when we did before, the average is going to be 1/2 the maximum current times the maximum voltage. So the power, the average power, 1/2 the voltage times the current. If you put in the definition for voltage based on current, you can get a much more useful to us equation. That the power average multiplied by the time is the energy you stored turns out to be 1/2 the inductance times the current squared. That should look familiar. The potential energy for a, you can see what I was thinking. I think I wrote capacitor a lot here by accident. For a capacitor, the potential energy it stored was 1/2 CV squared, right? You had to use that on the last test. For an inductor, instead of C, you have L, and instead of voltage, you have I, current. But it follows the same form. The energy stored on a capacitor is related to the voltage. The energy stored in inductors is related to the current. Why? Because the electric field depends on voltage. The magnetic field depends on the current. So it's easy to see these parallels between inductors and capacitors. Now, when used in a circuit, what did a capacitor do? Okay, it stored a charge separation, and as a result of storing that charge separation, it kind of kept the voltage from fluctuating as much. Remember, I talked about making an AC source, and it goes like this. And if we put a capacitor in there, the capacitor between ground and the voltage coming out, it will smooth it out. And so the capacitor helps to smooth out voltage. What do you suppose an inductor does in a circuit then? It helps to smooth out current, because the two are doing essentially the same job, but one's for voltage, one's for current. So I think that's the top of this next slide. Oh, nope, not yet. It's the top of the next slide. I got ahead of myself. Back to the energy stored. It stores energy in a magnetic field, and in terms of, if we substitute for the inductance, the equation for physical inductance, we get something that looks long and ugly. And you might wonder, why would I want something long and ugly? Please say you wonder that. The reason is, since it stores energy in the form of a magnetic field, it's going to be really useful to us, especially going into the next chapter, to know about the energy stored in a magnetic field. And so I'm doing this so I can work toward finding the energy stored in a magnetic field. Of course, your inductor can have different shapes. So what we do is we calculate the energy stored per unit volume. And I couldn't bring myself to put lowercase p, lowercase e for the energy stored per unit volume. And so I put the standard notation of lowercase u. Uppercase U is potential energy, lowercase u is potential energy per volume. That's the standard we use in physics. And so this here is the potential energy per volume. So I just took this 1/2 Li squared divided by the volume, substituted for L, so that's substitute for L, divided by the substitution for volume of a cylinder, since we have a cylinder when we wrap these, and we get the energy density is 1/2 mu watt n, the number of turns per length squared, times current squared. Now that still doesn't tell me the energy stored by a magnetic field. Still telling me the energy stored in the inductor, right? Well, we just need one more step. If we relate that the magnetic field for a solenoid is mu watt Ni, then this here is equal to B squared divided by mu watt. And so the energy stored in a magnetic field is the magnetic field squared divided by 2 mu watt. So that's an important outcome, one that we're going to look at in the next chapter, i.e. tomorrow. Okay, a very quick transient circuits. We talked about transient circuits with a capacitor. what happens? I charge up a capacitor. What does it look like, the curve for charging a capacitor? What did it look like? It looked like that. It asymptotes to being fully charged, and we learned the equation that the voltage was equal to one minus e to the minus t over tau times the voltage of the power supply we're charging it with. What was tau in this case? It has a name that tells you exactly what it is. Tau is the blank, blank, blank constant. It's the RC time constant. Tau is resistance multiplied by capacitance. So if you have a bigger tau that has a bigger resistance times capacitance, then it's going to be slower in charging. And likewise, slower in discharging. A smaller tau would be faster in charging and discharging. When we use an inductor in our circuit, instead of looking at voltage, we're going to look at, what do you think? The current. And the current is going to do the same thing. If I did, we don't say charging anymore for an inductor, but if I was doing the same as charging an inductor, and I had current here, it would look exactly the same. The equation would be exactly the same, except for an inductor, tau is L divided by R. So you just have a different time constant, but you have the same type of behavior. Now, I did not in any way go through and derive these equations. This here is showing a discharge rather than a charge. And so for the discharge, you have, well, that's showing the voltage, but it's still, the current does the same thing. Yeah, I'm not going to put the current equation here because that is a voltage discharge. So the voltage charge and discharge, they look just like they do for a capacitor. Here's the actual equation for the current for the capacitor. That's, I think I put voltage instead of current when I wrote it before, didn't I? Yes, I did. I wrote it wrong. Well, I'm not going to go back and change it now. The die is cast. It'll be on YouTube anyway. So we have the same types of equations for capacitors and inductors. This here is a quick summary showing the relationships. Notice U is used for potential energy here. It comes from a different textbook. The voltage proportional to charge for capacitors is proportional to the rate at which the current is changing for an inductor. The current can't change discontinuously for a capacitor. The voltage can't change. Got to think about this. Is that the way we said it? Yeah, those are reversed. I didn't make this. That came from a textbook. The current cannot change discontinuously for an inductor. The voltage cannot change discontinuously for a capacitor. I cannot believe I didn't even notice that last year. Yes, but this one here is for capacitor. Correct. Oh, I see. I missed the words can and cannot. It is correct. Sigh of relief. Okay. You can go down, see the rest of things. Energy stored is electric field squared or magnetic field squared, the time constants, and the equations. That was a very quick rundown. Now we're going to talk about the RLC circuits, such as what we're going to be doing here. A very large number of our circuits that we use in electronics are RLC circuits. Circuits that have resistors, inductors, and capacitors. And when you're doing an alternating current calculation, you have some slightly different things because inductors and capacitors don't behave the same as resistors. Resistors, the voltage is proportional to the current. We did an experiment with Ohm's law, right, where you studied that. For a capacitor, the current depends on the rate at which voltage is changing. Right? For a capacitor, you have Q is equal to VC. Well, if you do delta over delta T on both sides, that is current. So current is equal to C multiplied by the rate at which the voltage is changing. So that means if you have a rapidly changing voltage, you'll have a high current. A slowly changing voltage, a low current. Because of that relationship, if you have a sinusoidal alternating current, then the maximum voltage on a capacitor is equal to the maximum current divided by omega C. Now, the first question to ask is, hey, what is omega? We haven't talked about omega today. Omega is the angular frequency, or 2 pi times the frequency in hertz. So omega has to do with the frequency you're using. So the relationship between voltage and current, the maximum voltage and the maximum current, is inversely proportional to the frequency. So if you have a really high frequency, you're going to have a really small voltage. A really low frequency, you can have a much higher voltage. Now you'll notice that this is current times R. Here we have current divided by something. Well, we say that current divided by something is the same as current times 1 divided by something. And we call that 1 divided by something the reactance X. So we take this and we say for a capacitor, 1 over omega C is equal to X sub C. We call this the reactance, not the resistance, but the reactance. It looks like resistance because we have voltage max is equal to I max XC. That's supposed to be a C and it looks much like an L. It looks like resistance in the equation. It's going to have the same units as resistance, ohms, but we call it reactance because a resistance is absorbing energy. Remember, you have electrons going through a wire. The electrons are bouncing off of things and losing energy. So resistance has to do with losing energy. The reactance is called the reactance because the capacitor is reacting to having the current going through it. Now, as I pointed out this morning for the calculus-based class, technically current does not go through a capacitor. Current comes to one side of the capacitor, current leaves the other side of the capacitor. What actually happens to the capacitor? It builds up a charge separation. So there's no current through the capacitor, but there's current to it and current leaving it. As far as we're concerned, that's the same as having it go through. So we talk about it like it goes through. So with the capacitor, it's reacting to the current going to it and leaving it to create a bigger voltage. But it will return the energy. Unlike a resistor. Resistors won't return the energy. But the capacitor will, and that's why we call it a reactance. It just reacts to store energy and then give it back. Now if we look at the inductor line, the inductor, the one we just talked about, the voltage was equal to L times the rate at which the current changes. So that means that we could write this, the maximum voltage is the current times, and then we have omega L. Where do those come from? It's actually a quick step. I didn't do the quick step in class today, but it's a quick step with calculus. So we would define a reactance again for an inductor, but for an inductor, which starts with an I, we have omega L is equal to the reactance of the inductor, and V max is equal to I max XL for the inductor. So once again, the reactance acts like resistance, but it's storing energy. Now there is another piece to this. If I were to look at a voltage curve Where on a sinusoidal curve do I have the biggest slope? Sinusoidal curve, something like this. Where do I have the biggest slope? I have the biggest slopes where it's crossing zeros. It's positive there and negative there. Since my current is proportional to the rate at which voltage is changing, that means my current is going to be maximum here. Maximum current for a capacitor and minimum current for a capacitor. 9 degrees out of phase. Now actually, it turns out to be the other way, that there's a minus sign that's not shown in that equation, so it's actually like that. But you have maximum and minimum, and the 0 voltage for the capacitor is where you would have had maximum voltage for a resistor. In terms of an alternating current, we say that we have shifted the phase. The phase is the time to when we reach the peak of each sine wave. And so if you shift the phase, the time at which you reach the peak has shifted to a different time. And so the capacitor is out of phase. That is, the current through the capacitor is out of phase with the voltage. Actually, no, I guess it was correct because I wasn't looking at what I was plotting. But likewise with the inductor, the voltage is proportional to the rate at which the current is changing. You once again have an out of phase shift. So here's a graph showing the voltages for resistor, inductor, and capacitor, just like what you're going to be doing in lab today. Now I say all of this, when you do it in lab, you will see and you can compare. Was what I telling you the truth, or was I mistaken? So if you look on this graph, the solid magenta line is the voltage across the resistor, which is in phase with the current. And then the dashed blue line is the voltage across the capacitor. Now if we look at this, there is the peak for the current and the voltage across the resistor. Here is the peak, so that's time peak for the capacitor. This is time peak for the resistor. Which comes first, the time for the peak in the resistor or the time for the peak in the capacitor? The resistor came first. It came at 1/4 time period, whereas the capacitor came at 1/2 the period. So there's a difference here of 1/4 of a period. 1/4 of a period, if you put that in degrees, that's 90 degrees. So we like to say that there's a 90-degree phase shift between the voltage across a resistor and the voltage across a capacitor. And furthermore, because the time where the voltage across the resistor comes first, we say the voltage in the resistor leads the voltage in the capacitor. Or the voltage in the capacitor lags the voltage in the resistor. Now let's look at the inductor. Where does the inductor have its peak? Its peak is right here. Is that leading or lagging the resistor? It's leading. It comes first. And once again, it's 1/4 period between them. So we have the voltage in an inductor leads the voltage in a resistor, whereas the voltage in a capacitor lags the voltage in a resistor. Voltage in a resistor is the same as current in the current everywhere. They're not equal magnitude. It's the time when they lead, the time when they have their peaks that's the same. Because resistor, the voltage is proportional to current. Putting these two things together, we come up with a simple mnemonic that I hope all of my engineering students learned. Eli, the ice, got to write that in caps. Man, the lowercase words don't count. They're there to make a mnemonic. What counts is the Eli and the ice. The center of the Eli is L for inductor. The center of ice is C for capacitor. And then E stands for EMF, or voltage. I stands for current. And so the way to read these are the voltage in an inductor leads the current, because the voltage came first. The current in a capacitor leads the voltage. So that means that for the capacitor, this one is leading, this one is lagging. For the inductor, this one is leading, this one is lagging. This is E and I. So E leads I. This here is I. For the ice, it's I leads E. So that's a way of keeping those phases in mind. Now, a simple question. If I asked you what the voltage is between this point and this point, how would you answer? I have VL across the inductor, VR across the resistor, VC across the capacitor. So what is that voltage from the top to the bottom? Actually, let me put it in the order they come. It should be the sum of those three voltages. So just putting numbers on, let's say that this is 1 volt, 2 volts, and 3 volts. What do you get when you add those three voltages together? The simple mind says, well, 1 plus 2 plus 3 is 6. But that's not correct because they're not at 1, 2, and 3 at the same time. If you look here at time 0, this one's at 3, this one's at 0, and this one's at -1. And so at time 0, if you measure across there, you would measure a total voltage difference of 2 volts. And as you move on, you'll find different values. Here again, I'd measure total voltage difference of 2 volts. Here, you have to take each one and add them together. So you're going to have the total voltage is actually changing in time because you have those voltages are changing in time. So the total voltage is not going to be equal to each individual voltage if you take the peaks. But if you take it one instant, it will be. Yeah.
Isn't it just coincidence that the first two would be like 2, 2, and then -2, -2?
Yes, coincidence. The times that are on the quarter periods here are all the same value, but they're not the same value at all times. Yeah, because it looks like that would just be a constant, and it wouldn't be. Yeah, I noticed that as well. Okay, now we're going to have to do some phasor diagrams. Bridget came in to ask me about these as she was preparing for lab, and she got like the $10 tour. We'll try to give you more of the 10-cent tour here rather than the $10 tour, making it go quicker. We have these voltages that reach their peaks at different times, and we want to find some way to determine what the total voltage is going to be. So one way of doing it would be to take this graph that we had and try to figure out, okay, so at this time right here, I take this value plus this value plus this value, what does it give me? And do that at all places. Or I could do it mathematically here, and I have the total voltage is the voltage across the inductor. Here I've put the equation with the sinusoidal variation. This plus pi over 2 is because the voltage across the inductor leads the current by pi over 2. The voltage across the resistor, the voltage across the capacitor, because the voltage across the capacitor lags by pi over 2. That's why it has the minus pi over 2 there. And then I can add these together. Now, these three signs, I have to combine them somehow. Algebraically, we can. Algebraically, we can combine these three and get the maximum voltage times sine of the same frequency, but a new, what we call phase angle. That phase angle tells me when the total voltage is going to be 0. And so we can do this algebraically. Now, phasor diagrams are a way of showing how we did that algebraically. So we take, for our phasor diagrams, and we make a graph that shows the resistive voltage. It had a phase angle of 0 because the resistance was in phase with the current. And so we put this at an angle of 0 degrees. The phase is 0 degrees for the resistance. For the inductor, it had the plus pi over 2, or plus 90 degrees. So the inductor is shown at a phase angle of 90 degrees. And the capacitor is shown at a phase angle of minus 90 degrees. So we make this phasor diagram with those angles based on if it's leading or lagging or in phase with current. And then we add these as if they were vectors. We call them phasors for phase vectors. They're not actual vectors. We don't have a direction involved here with our currents. Instead, it's a phase, how long it is until they reach their peaks. But we add these, and if we just take these three vectors, you add them tip to tail. This is showing the, this is the way I like to do it. I like to show VC, VR, VL. I like to put the resistance one between the capacitor and the inductor because then I can see each one separately. And how do I get the resultant when I add these up? Go from where to where? Go from where I started to where I finished. So there's the V total. That V total tells me what the maximum voltage I'm going to get over the entire circuit is. As you can see from my picture, my V total is smaller than my VL by a fair amount. It's possible to put in, I'm going to have you put in 10 volts rather than 6 volts. In fact, let me hit save now just in case I forgot to do it. I've been working with the one you're going to be doing. Okay, so now I've saved it. I'm going to have you use 10 volts instead of the 6 volts it says in the lab guide. But you could have the voltage across the inductor or the capacitor be 12, 15 volts. It's perfectly possible. Why is that possible? Because at the time when the capacitor has a voltage of, let's say, plus 15 volts, the inductor has a voltage of, let's say, minus 20 volts. You add those two together and it's just minus 5. That's within my 10, right? 10 volts. It's going to go from plus 10 to minus 10 the way we're doing it. And so that's perfectly acceptable to have a larger maximum voltage across the inductor than a maximum voltage across the entire circuit. Now, with these phasor diagrams, I was talking with Bridget, you have EM is equal, or E is equal to the EM, what we get from this, times sine of omega t plus V. With time, that voltage is changing. It's getting bigger and smaller, changing in a sinusoidal fashion. And so we've just found the peak here. The angle that goes right here, we just get from using trigonometry. You take the opposite side, which is VL minus VC, divide by the adjacent side of VR, and that tells you what the phase angle is. You're going to be doing this in your lab today, so of course it's kind of important that I explain what that is. That tells us about how much the time shift is going to be, because if you find the time when omega t plus phi is 0, that tells you when you're at your peak. Actually, that tells you when you're at 0. But it tells you about your relative phase. Now, we learned that the maximum value for resistance was IR. The voltage cross resistance maximum value was IR. For a capacitor, the maximum value was IXC. And for an inductor, the maximum value was IXL. And we just saw from the previous page that XL, well, that the voltage across the inductor was plus 9 degrees, and voltage across the capacitor was minus 9 degrees. So using trigonometry, using Pythagorean theorem, the total voltage is the voltage across the resistor max squared plus the voltage across the inductor minus the voltage across the capacitor squared, and then square rooted. Well, if we substitute in Ohm's law using resistance and reactance, notice we have I everywhere. So I can factor that I out, and then I have square root of R squared plus parenthesis XL minus XC and parenthesis squared. This here we call the impedance. So we have a couple new words that are like resistance. There was first reactance. Reactance was how an inductor or capacitor reacts when you have a changing current. Impedance is combining the effects of resistance and reactance. I remember when I was a little boy talking to my uncle who worked in electronics industry and trying to figure out the difference in impedance and reactance. And yeah, he didn't know the difference. At least he couldn't explain it to me. Made me sad. Now I understand when you talk about impedance, that includes reactance. Reactance is one way of responding to a current. Resistance is another way. The fundamental difference between reactance and resistance is resistance absorbs energy, reactance stores energy. And impedance is talking about anything that's going to affect voltage if current flows through. So you are going to be making plots of things like this. So it's important to have this understanding. Something else that's really curious here, you have XL is equal to omega L. So if omega increases, that is if your frequency increases, what happens to XL? It gets bigger. But XC is equal to 1 over omega C. So if omega gets bigger, if the frequency gets bigger, what happens to XC? It gets smaller. That means that there's a crossover point where this term in parentheses will equal 0. When that term in parentheses is equal to 0, your impedance is going to be a maximum. Any other frequency, the impedance will drop. Or excuse me, maximum? Yeah, it'll be a minimum, not a maximum. Any other frequency, the impedance will increase. If you have a series circuit, it's the way I just said. If you have a parallel circuit, it's the opposite. And so we call the frequency where these equal each other, when XL equals XC, we say we have resonance. Resonance because we have our minimum Z. And so, of course, you can very quickly, I'm not going to do it for you, it actually I think is in the lab guide, but you're going to have to calculate what that resonant frequency is for your experimental setup. And then you're going to have to explore and see if it really does what these next two slides show. Okay, the next two slides don't show it. It's after must be the next two after this. The phase angle can be calculated not just from impedance, but also from the resistance and reactance. The phase angle is the voltage across the resistor, well, cosine of the phase angle, voltage across the resistor divided by the total voltage, or resistance divided by impedance, or you can go to tangent. Tangent of the phase angle is the reactance divided by the resistance. You can use any one of these. You're going to have to calculate what that phase angle is So any one of these will work. Very quick blanket statement. If you just have a resistor and a capacitor, just a resistor inductor, or just an inductor capacitor, everything we've talked about is still going to work. It's still going to be the same thing. Please be the resident. Okay, we're not going to do that problem because I've already been in here for 50 minutes. I'm not going to do that right now. The average power depends on that phase angle. If you have an inductor, how much power does an inductor use in an AC circuit? Another way of asking this, what does an inductor do in an electric circuit? Stores energy in a magnetic field. It didn't use the energy, it stored it. And it gives it back. So it doesn't actually consume any energy. So an inductor in an electric circuit, the average power is 0. An inductor doesn't use any power. Likewise, a capacitor in an electric circuit, the average power is 0. It doesn't use any power. It will absorb some to store energy, but then it will give it back. Resistors use power. So now you have in your house something like a refrigerator. A refrigerator has an electric motor. An electric motor is made by having a loop of wires to make a magnetic field. Well, what's another word for a loop of wires? A coil, an inductor. So the electric motor has a pretty strong inductance, which means that that electric motor is going to absorb energy, give it back, absorb energy, give it back. What that does is it shifts the phase angle, and the power company doesn't know that it's given back the energy. It just knows that you've had some current and you have a voltage. And so the power company charges you for the energy that's being stored and given back in that coil, even though you're not really using it. Much like owning it is just spilt upon the ground. That is, it's returned to the ground. So that power, you don't want to get charged for something you're not using, right? So ideally with your refrigerator where you have this big inductor, that gives you an inductive phase angle. That gives you a phase angle that's bigger than 0. Because remember the inductance had a 90-degree phase angle? Well, you want something that's going to give you a capacitive phase angle, a negative phase angle with that, so you can bring the angle down to 0. So if you put a capacitor in series with that inductor, it's not going to use any power either, but it's going to change that phase angle so your actual power is closer to voltage times current. And so then you get charged only for the power you're using, and you're not wasting power. So you can actually save a fair amount of money, and I am sure that when they make refrigerators, they actually do this, by having a capacitor in there with the electric motor to make the phase angle come out to be close to 0, so that your total power and the apparent power, the VI is your apparent power, and your total power is the VI cosine phi, so that those are very close to each other. Because you get charged for VI, and you only use VI cosine phi. Okay, I believe that, oh no, I have the resonance picture still. The resonance pictures. Remember I said that depending on the frequency, your impedance changes. And so here we have different frequencies on this axis. And you can see that the current that is drawn by a circuit varies with the frequency. So that when we have the minimum impedance, we drew the maximum current. And that was when we were in resonance. There's another slide that just has that picture. I'm just going to change to another slide because it just has the picture a little blown up. You're going to reproduce this curve with your experiment. After you finish the experiment, the main part, you're going to go through and you're going to find first what the resonant frequency should be. And then you're going to go from 50% below that to 50% above that. You notice this is a logarithmic axis on the bottom, not a linear axis. For it to look symmetric, you need to use the logarithmic axis down there. You're going to change the frequencies and see if the current, you'll measure the current simply by measuring the voltage across the resistor, see if that actually peaks at the frequency that you predicted based on your measurements. So we're going to examine that resonance. This is the calculation for resonance, but like I said, I think it's in your lab book, and I have no need to do that. Let's take ourselves a 5-minute break, just so the people who've been sleeping can wake up, and then I'll go over the actual lab.